Good day, everyone. Today we'll discuss measuring errors. In any numerical analysis, errors will arise during the calculations. To be able to deal with the issue of errors, we need to identify where the error is coming from, followed by quantifying the error, and lastly, minimize the error as per our needs. In this lesson, we will concentrate on quantifying errors. We need to measure errors because we need to determine the accuracy of numerical results and to develop stopping criteria for iterative algorithms. True error is denoted by capital E sub t is the difference between the true value in a calculation and the approximate value found using a numerical method, etc. So the formula for true error is equal to the true value minus the approximate value. Next is the relative true error. It is denoted by epsilon sub t and is defined as the ratio between the true error and the true value. The formula for relative true error is equal to true error divided by true value. Example number 1. The derivative f prime of x of a function f of x at a particular value of x can be approximated by the equation as shown below. Find the true error and the relative true error for f of x is equal to 7 e raised to 0.5x at f prime of 2 with h is equal to 0.3. To solve this, the approximate value and the true value of the function must be calculated first. The approximate value of the function at f prime of 2 is f prime of 2 is equal to f of 2, which is your x, plus 0.3, which is your h, minus f of 2 divided by 0.3. This is now equal to f. So 2 plus 0.3, we have 2.3. Then minus f of 2 divided by 0.3. And then substituting to the function of x, which is 7e raised to 0.5x, we now have 7e raised to 0.5, and then the value of x, which is 2.3, minus 7e raised to 0.5 times x, we have 2 divided by 0.3. And then we now have 22.107 minus 19.028 divided by 0.3. This is now equal to 10.263. The exact value of f prime of 2 can be calculated by using the knowledge on differential calculus. We have f of x given is equal to 7 e raised to 0.5x, and then the derivative of this f prime of x, we have 7 e raised to 0.5x times the derivative of 0.5x, that is 0.5. This is now equal to 3.5 e raised to 0.5x. Substituting f prime of 2, we now have 3.5 e raised to 0.5, then the value of x is 2. This is now equal to 9.514. Therefore, the calculated true error for this is now equal to E sub t is equal to the true value, which is 9.514, minus the approximate value, which is 10.263. This is now equal to negative 0.749. Next, solving for relative true error, that is equal to the true error, which is negative 749 divided by the true value, which is 9.514. This is now equal to negative 0.07873. Or in percentage, the relative true error is this value in here times 100%. So that is negative 7.873%. Or we need to also calculate the absolute relative true error. Absolute relative true error, that is absolute relative true error is equal to the absolute value of negative 0.07873. This is equal to 0.07873, or that is in percent, we have 7.873%. Approximate error is denoted by capital E sub A. It is defined as the difference between the present approximation and previous approximation. Approximate error is equal to the present approximation minus the previous approximation. Next is the relative approximate error. It is denoted by epsilon sub A and is defined as the ratio between the approximate error and the present approximation. That is, relative approximate error is equal to approximate error divided by the present approximation. Example 2. The derivative of the function f of x at a particular value of x can be approximated by the equation shown below. For f of x is equal to 7 e raised to 0.5x at x is equal to 2, find the following. A, we're going to solve for f prime of 2 using h of 0.3, f prime of 2 using h of 0.15, the approximate error for the value of f prime of 2 for part B, and the relative approximate error using values from 0.3 and h of 0.15. First, we're going to solve for f prime of 2 using h of 0.3. That is, we have f prime of 2. This is equal to f of 2 plus h of 0.3 minus f of 2 divided by 0.3. This is now equal to f of 2.3 minus f of 2 divided by 0.3. And then substituting the function, we now have 7 e raised to 0.5 times x of 2.3 minus 7 e raised to 0.5 times x of 2, then divided by 0.3. Simplifying this, we have 22.107 minus 19.028 divided by 0.3. Therefore, f prime of 2 at an h of 0.3 is equal to 10.263. Next, for f prime of 2 using an h of 0.15, we have f prime of 2 is equal to f of 2 plus your h of 0.15 minus f of 2 divided by 0.15. This is now equal to f of 2.15 minus f of 2 divided by 0.15. This is now equal to, now the function is 7 e raised to 0.5 times the x value, we have 2.15 minus 7 e raised to 0.5, we have value of x, which is 2, divided by 0.15. This is now equal to 20.51 minus 19.028 divided by 0.15. f prime of 2 is now equal to 9.880. Next, for letter C, we're going to solve for the approximate error for the value of f prime of 2 for part B. We have to solve for the approximate error. that is E sub A is equal to the present approximation. We have 9.880, that is from part B, minus the previous approximation, that is from part A. We will have an H of 0.3, that is 10.263. Therefore, your approximate error is equal to negative 0.383. Next, we're going to solve for the relative approximate error using the values from h is equal to 0.3 and h is equal to 0.15. Solving for relative approximate error, that's equal to the approximate error, that is negative 0.383, divided by the present approximation. We have 9.880. This is now equal to negative 0.038765. And then as a percentage, your relative approximate error is equal to this one times 100%. We now have negative 3.8765%. Also, we can determine the absolute relative approximate error, that is equal to the absolute value of relative approximate error is equal to the absolute value of negative 0.038765, that's equal to 0.038765, or in percentage we have 3.8765%. That ends our lesson on measuring errors. Thank you.